Lecture 4, Vector Properties and Vector Addition. This lecture relates to Chapter 3 of your textbook. We're of course already familiar with vectors. Recall the race between the tortoise and the hare. We see the longer velocity vectors are representing that the hare is going faster than the tortoise. The longer velocity vectors are consistent the same length, showing us the hare is in uniform motion, a faster uniform motion than the tortoise. If the motion is following a curved path, our vectors are still straight. The velocity vectors are longer where the object is moving faster, as it's slowing, as it's taking around the curve. If it's a ball going from Jake, tossed up and going to Jim, the ball's up and over, and as it's going up, it's slowing, and we see that from the vectors. We also see the changing direction of the vectors tells us the changing direction of, let's say, the ball being tossed to Jim. The vectors are never drawn in a curve. Vectors are always straight. The length of the straight vector is the amount of speed or displacement or force or acceleration or whatever it presents. Here, these velocity vectors must be straight. Their direction is ever changing, represented by a few vectors here, to imply the curved path. There are many things that we don't need vectors for that we talk about in physics. Mass, how much matter, how much mass or inertia something has, doesn't need a property of direction. Your certain amount of kilograms, whether you turn left, you walk right, you're 70 kilograms, not 70 kilograms up or 70 kilograms south. You are just a number, a scalar, a numerical value. We'll learn energy is just an amount. You don't have more energy going to the left and less energy going south. You've got energy. You have a numerical value, regardless of whether you're walking to the left or walking south. There is no direction that goes with energy. It's not a vector. Like mass, it's a numerical amount. It's a magnitude or a scalar. In this illustration from your textbook by night, different parts of a room are at different temperatures. This doesn't imply that temperature is a vector. You don't have 20 degrees to the south and 13 degrees left and 18 degrees going up. You can have different temperatures, different values, different numerical results in different parts of the room. And time is not a vector either. What time is it? It's just a number. You could argue the time is always going forward, but since that's a consistent direction, we just say its time is just progressing. It doesn't need a necessary direction to make it a vector. You can't take a left turn into yesterday. Things that do need direction, position. If I am 10 feet, I have to say I'm 10 feet from something, from an arbitrary origin. I'm 10 feet from a door. I'm 3 feet from a wall. I'm 1 mile from the downtown. I'm 2 miles from the bus stop. All these are numbers with direction. Position necessarily needs to be described with a vector describing the amount, the positions from some origin. Velocity, I'm going 60 miles an hour along the highway. Am I going 60 miles an hour going to the right or 60 miles an hour in the opposite opposing lane going to the left? Am I going 80 miles an hour to the north or am I going south on the 80 miles an hour? That makes it a velocity. You'll see momentum and force also need to be described by vectors. There are amounts, scalars, numerical amounts, numerical values, or magnitudes along with a direction. If you push or pull on something, it's a force. But if you push against the motion or with the motion, you can speed something up or slow it down, respectively. How you push on an object is important. You can push on an object a certain amount and it can tip the object. You can push on the object the same exact amount at a different location and make the object speed up, slow down, or do something or deflect. Where you push on it, the direction the push is important. So force is described by a vector. Notice that in this second illustration, if we consider the air to be the motion of the air, the gas particles of the air, if we represent them in terms of the velocity of the air particles, Where the air is buzzing around, moving faster, where the velocity is greater, it corresponds statistically to where the temperature is greater. So something that's a scalar temperature can be composed of a large amount of vectors, velocity vectors. Hot gas is gas that has more speed. There's greater velocity for the hot gas. For the gas particles, the vectors are on average pointing in no particular direction, unless there's some kind of a drift or wind. The gas particles may be going faster, but they're going faster in all directions. So vectors can statistically sum up to be scalars. So these two things aren't entirely independent. Temperature depends on things that have to be described by vectors, such as the motion of the gas particles. A vector only has two properties. We draw a vector with an arrow. The arrowhead is the direction of the displacement, the direction of the velocity, the direction of the speed, the direction of acceleration, the direction of the force, the direction of the push and pull. And the length of the vector is the length of the arrow is the magnitude of the vector, the amount of speed, the amount of displacement, the amount of acceleration, the amount of push or pull. A vector only has these two properties. We call this length, magnitude, numerical amount the scalar. Let's do an example, adding displacement vectors to show vector addition. Jenny runs 3 miles to the east, and then 4 miles to the north. We add these two displacement vectors by the head-to-tail method. 4 miles to the north, the tail of the displacement vector, that's 4 miles to the north, starts, as we see, at the head of the 3-mile displacement vector. So 3 plus 4, the tail of displacement vector 4, this tail is at the head, the end of the 3-mile displacement vector. The result of 3 plus 4 in vector addition is not 7. It's a 3, 4, 5 triangle. The overall displacement is 5 miles when you go 3 miles to the east and 4 miles to the north. We use Pythagoras' theorem to see 3 squared plus 4 squared is equal to 5 squared. Using SOHCAHTOA, sine, cosine, and tangent, we can find the angle of the displacement whose magnitude is 5 from the start or initial to the finish. Notice the tail of 5 is at the tail of 3, and the head of the vector 5 is at the last head, the head of 4. By the same head-to-tail method, if Johnny runs 1 kilometer to the west and then 1 kilometer south, the net displacement is adding 1 plus 1, using Pythagoras' theorem, 1 squared plus 1 squared is equal to 2. And so the net displacement is root 2. Vectors such as this velocity vector doesn't have to be along a horizontal or vertical, along an east or a north. It can be at an angle. So here's 5 meters per second, such as an object that's projected or thrown 5 meters per second at an angle. This velocity vector, v initial, could stand for a car going to the right with some initial speed. If the car goes faster as time goes on, then we draw the velocity of the car later, or final, vf, to be longer to represent it went from, say, 30 miles an hour to 50 miles an hour. But how did it go from 30 to 50? Well, it changed its speed, or delta v, where delta v is the increase in the speed. But that's just another vector. So to go from 30 miles an hour to the next vector, 50 miles an hour, we must have changed the speed or added a delta v of 20 miles per hour. So this would be the vector addition, v initial plus delta v, equals 30, for example, plus 20 equaling 50 miles per hour in our example. We've added these v initial and delta v vectors head to tail to sum to the final velocity vector, whose length is the same as the sum of the v initial plus delta v. If our 30-mile-an-hour car is represented by this velocity vector initially, and then it slows down by 20 miles an hour, we add v initial plus the change in speed plus the change in velocity. But our change in velocity is opposite the direction. It's representing a reduction in speed as being v initial is being reduced. So I add delta v, v initial plus negative delta v, or v initial minus delta v, to equal our new v final. This is the head-to-tail method, where delta v's tail is again at the head of v initial, and our v final vector, its tail starts at the tail of v initial, and its head points at the second vector to be added, the head of delta v. This is how I can represent directions being changed. 30 miles an hour, the direction, say, going to the east, and then 30 miles an hour to the southeast, I've changed the velocity to a new direction. Again, this is the head-to-tail method, v initial plus delta v, where delta v's tail is at the v initial's head, and v final's tail is at the tail of v initial, and v final's head is at the head of the second vector to be added, delta v. Two vectors, a and b. They could be velocity vectors, displacement vectors, any vectors. How do we add these vectors? Vector a plus vector b, we take the tail of b and place it at the head of a. A plus b, that net vector, the net vector a plus b, its tail is at the tail of a, and the net vector a plus b, its head is at the head of the second vector, the last vector to be added. This arrow here can also represent vector b. It has the same length or magnitude and it points in the same direction, so it can stand for the same vector. We can move our vectors around or slide them around. So b plus a, a's tail is now at the head of b, and b plus a, the net vector's tail is at the tail of b, the net vector's head is at the head of a. We see a plus b, the net vector, is the same as b plus a. It does not matter the order, whether it's a plus b or b plus a. It does not matter the order you add vectors. The result is the same. Even if it's three vectors. Vector a again, a new vector c, tail of c, is at the head of a, and vector b's tail is at the head of c. This is our head-to-tail method. The result, or net vector, a plus c plus b, that net vector's tail is at the tail of a, and the head of the net vector is at the last vector to be added, the head of b. Again, it doesn't matter the order. That same vector b plus the same vector c plus the same vector a gives us the same result. So whether it's a plus c plus b or b plus c plus a, the net vector is the same. The net vector's tail is at the tail of b. The net vector's head is at the last head of the vector a, the last vector to be added. And whether it's a plus b plus c, we would still get the same net vector. Add vectors in any order. Add them in the order that makes your calculations easiest. Answer this question on Blackboard to practice vector addition between vectors p and q. Which of these choices results in the correct vector? Add vector p plus q by the head-to-tail method. The net results should have the net vector's tail at the tail of p and the net vector's head at the head of q after p and q have been added head to tail. Scaling and summation, if vector A is to be multiplied by a factor of 2 or doubled in size, then vector 2A, a vector of twice the length, should be drawn to be twice the length if it has twice the magnitude. If a vector has 3 times the magnitude, it should be 3 times as long. If it has 3 times the magnitude and in the opposite direction, -3 times A, then it should be 3 times as long in the exact opposite direction. A positive vector and a negative vector point in the exact opposite directions. If I want to add vector A plus negative vector A, they are the same magnitude, same length arrows, but the exact opposite direction. So A plus negative A is A minus A, vector subtraction, which equals 0. Our net vector starts at the first guy's tail, A, and the head goes out to the last guy's head to be added, negative A, which is at the same location as the initial. Practice vector subtraction, vector P minus Q, which you can think of as P plus negative Q. Again, we have vector P and Q. We add vector P and Q by the head to tail method, but we're adding P plus negative Q. The negative Q vector is the same as vector Q on the screen, but in the opposite direction. Add that negative Q vector by the head to tail method. So negative Q's tail is at the head of P, and the net vector's tail is at the tail of P, and the net vector's head is at the head of negative Q. Do so and pick your choice and submit it on Blackboard. If a vector points at an angle, we can break that vector into what we call components, where the vector is now the hypotenuse and the components become the sides of a right triangle. Our velocity vector is the hypotenuse, and we use Pythagoras' theorem and sine, cosine, and tangent to relate the sides and the angles of a right triangle. The amount of velocity in the negative x direction is v cosine times the angle. The amount of velocity in the positive y direction is v sine of the angle of 40 degrees. This vector, which could be a velocity vector, b could be displacement or force or any vector, we can show it to be the sum of two vectors which we call components, how much b points in the x direction and the y direction. I can break b down into the addition of any vectors I choose. Breaking v down to show it's the sum of two vectors bx plus by, to show it's built from these components, can sometimes be useful. How much is b pointing in the x direction or the horizontal? How much is this vector pointing up or north or vertical? Submit your answer to Blackboard to express this vector in its components. We list the scalar components as x, comma, y, the amount of the magnitude in the x direction, comma, the magnitude in the y direction. Submit your choice on Blackboard. Submit your choice on Blackboard for this question. What is this vector represented in its x and y components? What's the magnitude in the x, and what's comma the magnitude in the y component? Use sine, cosine, or tangent to figure out the magnitudes of the x and y components. Submit your answer on Blackboard. Here, vector A, we want to relate to a line at an angle or an incline, such as a ramp. How much is vector A pointing along the incline, or parallel, A parallel, or A in the x direction, if you want to call the x direction along the incline or along the slope or ramp? And how much is vector A pointing perpendicular, or in the y direction? from our incline. These would be convenient components to represent vector A relating to this incline. For example, if we have an acceleration vector, well, if the acceleration is from gravity, or A free fall, then gravity's acceleration has a component along the direction or parallel the incline down the ramp. How much is gravity accelerating the object parallel or down the ramp is a component of gravity's acceleration. That would be a useful component to know the acceleration parallel by gravity along or parallel to the incline. A parallel here would be equal to A of free fall times sine theta. I can take vector B and break into components x and y, horizontal and vertical, for example. But I can take that same vector B and express it in terms of components at other angles. If A is parallel to an incline, as we just saw, and B is, say, perpendicular to an incline, as we just saw. Or I can express vector B as two components perpendicular to a different slope. I can express vector B as the sum of any vectors I would choose, or the sum of two components in any orientation. I just re-express vector B in components that are convenient for the context. But the rules of mathematics, Pythagoras' theorem, still apply. The components x squared plus y squared still equals the vector's magnitude squared b squared. A squared plus b squared also still equals the same as the magnitude of the vector b squared. As we see, we can take a vector and express it into its components represented by coordinate systems, which you are free to choose depending on convenience. We often measure angles from the x direction and say it's from a horizontal. Since coordinate systems, or the direction of the components that we express vectors in, can be a variety of orientations and can be arbitrarily expressed, we have a general notation called unit vectors, which is a vector of magnitude 1, hence the unit of the unit vector. So AX, we say, is a vector of length, magnitude, numerical amount, AX, in the I hat direction, where I hat direction would be equivalent to saying it's in the direction of X, and J hat would be equivalent to saying it's in the direction of Y. So a vector can be decomposed into its amount AX and AY, and its amount AX and AY. AX points in the I hat direction, AY points in the J hat direction. I hat and J hat can be at various angles, as we saw with inclines and slopes. Submit your answer on Blackboard to express vector C into its components. How much is C pointing along the x direction and the y direction at the components in the Cx and the Cy? The amount that points in the Cx direction can be read off these axes, and the amount of vector C in the y direction can be read off this coordinate system. The amount in the x direction would be the amount times I hat. The amount that C points in the y direction would be its amount in the J hat direction. Submit the best answer on Blackboard. Again, we can add vector A plus B by our head-to-tail method. We can do so by breaking vector A into its components and vector B into its components, and then adding those components. vector A's component in the y and the x direction, vector B's components in the x and the y direction. A plus B, we'll say, is vector D, where vector D is made up of AX plus BX, and vector D is made up of AY plus the exact opposite vector BY. The component of B in the y direction cancels the component of A in the y direction, and so A plus B is the same as just looking at the components in the x direction of A and B. For an example, a practice quiz problem about adding vectors, displacement vectors. If you walk 50 meters to the north, and then you turn from the north 60 degrees to your right, and walk another 40 meters, and then turn again 30 degrees, and walk another 20 meters, how far and what angle are you from where you originally started? This difficult problem can be analyzed by drawing displacement vectors and breaking those vectors into components and adding the components to find the overall displacement or net displacement vector and what angle it points from our horizontal or x direction. We'll say these three displacements are A, B, and C, and our net vector, adding up these three displacement vectors, we'll call vector D. Here's 50 meters to the north, represented by displacement vector A, turns 60 degrees from the north and walks 40 meters, represented by displacement vector B, whose tail is at the head of A in our head-to-tail method, and then turns 30 degrees from that 60-degree direction, for a total of 90 degrees from the original north direction or to the east, and then walks 20 meters. Breaking up these vectors into components, we only have vector B's components in the y and the x direction. And so the overall displacement is A plus by and bx component, which is still just a vector, added to vector C. The overall amount in the x direction, bx plus c, and the overall displacement in the y direction, a plus by, is equal to our overall displacements component in the x and y direction, dx and dy, which yields our overall displacement from start, the tail of A, to finish, the head of the last vector, C. Again, we can find the amount of displacement, dx squared plus dy squared, is equal to d squared. The angle of displacement from the horizontal can be found by either sine, tangent, or cosine. This concludes vector addition.